Hey everyone, and welcome. Today, we're going to tackle a big name from calculus, the mean value theorem. And I know, the word theorem can sound a little intimidating, but trust me, the main idea is something you already get, especially if you've ever been in a car. So let's actually start there. So really think about this for a second. You get in your car, you hit some traffic on your way to the highway, then you speed up, maybe slow down again, and you finally get where you're going. You look at your trip computer, and it says your average speed for the whole trip was exactly 60 miles per hour. So here's the question. Does that guarantee that at some single specific moment, your speedometer needle pointed exactly at 60? What do you think? The answer is, yep, 100% yes. And that simple, intuitive idea that your instantaneous speed must hit your average speed at some point, that's literally the entire foundation of the mean value theorem. It's what we call an existence theorem. It doesn't tell you when or where it happens, but it gives you an ironclad guarantee that it must happen at least once. Okay, so how do we take this idea from the highway and translate it into the language of math? Well, in calculus, that means we're moving from speedometers to graphs, where we can actually see how these different rates of change look and behave. Think of this graph as your car trip. On the left, we've got the average change. That straight line connecting the start and end points is called a secant line. Its slope represents your average speed over the entire trip. But on the right, you see the instantaneous change. That's the slope of the tangent line, a line that just kisses the curve at one single point. That's your speedometer reading at one exact moment in time. And here it is, the formal theorem. Now, I know it looks like a bunch of math speak, but let's break it down. Look at the right side of that equation. That fraction? That's just rise over run between the start and end points. That's the slope of our secant line, our average speed, and on the left side, f prime of c, that's the derivative, the slope of the tangent line, our instantaneous speed. All the theorem says is that as long as your function is continuous, meaning no jumps or holes, and differentiable, meaning no sharp corners, there's got to be some point c where the instantaneous slope is the exact same as the average slope. All right, enough theory, it's way more fun to see this thing in action. Let's actually try to find that guaranteed point c for the function f of x equals the square root of x on the interval from 0 to 4. Let's get our hands dirty.
Okay, we're just going to follow the recipe. Step 1, let's find the average slope across the whole interval from x equals 0 to x equals 4. A little bit of algebra, and we get 1/2. Simple enough. Step 2, find the formula for the instantaneous slope at any point. That's just the derivative, which for this function is 1 over 2 times the square root of x. Now for the magic. The theorem promises there's a point c where these two are equal. So let's set them equal to each other and solve.
And boom, we solve it out, and we find that c equals 1. Now we're not quite done. There's one last crucial check. Is our answer, c equals 1, actually inside the interval we started with, between 0 and 4? Yes, it is. See? The theorem held up. It guaranteed a spot, and we found it. Now, this is where it gets really interesting. What happens when the guarantee is off? Those two conditions we mentioned, continuous and differentiable, they aren't just suggestions, they're hard and fast rules. So let's see what happens when we try to break one. This is a classic trap that a lot of calculus students fall into. Let's try to run the exact same process on a different function, f of x equals 1 over x, on the interval from -1 to +1. At first glance, this seems pretty straightforward, right? All right, let's just go through the motions like before. The average slope between our endpoints is 1. Easy. The derivative, our instantaneous slope, is -1 over x squared. Okay, now, we set them equal to each other, and we solve, and get, wait a second, we get c squared equals -1? Hold on. Stop everything. You can't square a real number and get a negative. That's impossible. The math literally just broke. But the mean value theorem is supposed to be a guarantee. So what happened? What did we miss? And here is the aha moment. This is exactly why those conditions matter so much. Our function, 1 over x, has a massive vertical asymptote, a huge break in the graph, at x equals 0. And where is x equals 0? It's smack badab in the middle of our interval. Because the function wasn't continuous on the whole path, the very first condition of the theorem was violated. The guarantee was void from the get-go. So here it is, the number one thing you have to remember. These are the MVT's golden rules. You have to check them first. Is the function continuous on the closed interval? Is it differentiable on the open interval? If the answer to either of those is no, then all bets are off. The theorem simply doesn't apply.
So let's zoom out and bring this all home. What's the big, powerful idea here? Why is the mean value theorem so important in the world of calculus?
This quote just nails it. The theorem is the fundamental bridge that connects the big picture, average behavior of a function to its specific, instantaneous behavior at a single moment. And this guarantee is more than just a neat party trick. It's a critical tool that's used to prove some of the other biggest ideas in calculus, like the fundamental theorem of calculus itself. So the next time you're on a road trip and you glance at your average speed, remember the mean value theorem. It's not just some abstract idea in a textbook. It's happening right there on your dashboard, guaranteeing that somewhere along your journey, for at least one fleeting instant, you were going that exact speed. For every average, there is a guaranteed instant.